Here we are at the intermediate value theorem from our 1.4 number 2 set of notes. Now suppose that f is a continuous function on the closed interval on a and b. And here's a, here's b. We can see that it is in fact a closed interval because as we look at our endpoints, we see that they are solid and filled in. So as a result, we do end up with that closed interval. And as you guys can see from the graph, it is in fact a closed interval. There's no holes or vertical asymptotes. It is pretty smooth and just kind of goes from A to B. Now, the intermediate value theorem pretty much just says that there has to exist some C value such that when you plug it into the function, there's at least one value C such that when you plug it into the function, you end up with a particular Y value that's in between f of A and f of B, as long as we are in between this interval A and B. All right. So again, this first graph would just show an image where we see exactly one value happening. But what the intermediate value theorem pretty much just says is that there has to be at least one of these C values where we end up with that Y value that we might be hoping for. The second graph, we see actually a bunch of different C values that we're looking for. Again, here is that line Y is equal to W. Oh, it's written over here. And we can see obviously that in this interval between A and B, it is continuous. We do include the endpoints, and that there are several C's. Here's one, here's another, such that when you plug them into the function, you end up with the exact same Y values. So here they are, as you guys can clearly see. But again, the intermediate value theorem says that there is at least one C value such that it'll work out. Now, kind of a corollary along with this is if you were to suppose that f is a continuous function on this interval A and B, and f of A and f of B actually have opposite signs of one another. So this is just a really quick sketch of a graph that has that. It doesn't necessarily have to be where f of A is negative and f of B is positive. As long as they have opposite signs of one another, then this corollary will actually uphold. As we see in this example, though, we will see that f of A happens to be negative and f of B happens to be some positive Y value. And as a result, there has to be this backwards E simply stands for there exists at least one value C that is inside of this interval between A and B. Oh, we cannot include the endpoints though, so just want to make that really clear. So there's one value C inside of this interval between A and B. In other words, this is considered to be like your X value, such that f of C, in other words, when you throw that C value into the function, you notice that it will in fact come out to be equal to 0. And here is that graphical representation of that actually occurring at. We see that C is in between A and B. As long as one of these guys is negative and the other is positive, then there has to be some point C where it's equal to 0 when you plug it into the function. Now, this is really going to help us out when we're looking at example 7, because it says given the function is equal to f of x is equal to x cubed minus x minus 2, determine if there is some C value where it's equal to 0 on this interval between 1 and 2. Well, as we can see, we have this function, and it is in fact a polynomial, and we know that from our previous definitions that polynomials are continuous from negative infinity to infinity. So we're just going to go ahead and say that f of x is in fact continuous on, because it's continuous on negative infinity to infinity, well, we're only specifically looking at this interval between 1 and 2. And as a result, because 1 and 2 is obviously in between negative infinity and infinity, we can then just say that f of x is continuous on the interval between 1 and 2 because it's obviously included inside of that massive interval. So as a result, f of x is obviously continuous. Oh man, spelling's way off. Is obviously continuous between that. Now, if we look a little bit more carefully, let's go ahead and find the value when we throw 1 into that function. If we throw 1 in there, we end up with 1 cubed minus 1 minus 2. 1 cubed comes out to be 1 minus 1 minus 2. 1 minus 1 is just 0 minus 2. We end up with a y value of negative 2. Alternatively, if we go ahead and throw in our upper bound here, 2, we end up then with 2 cubed minus 2 minus 2. 2 cubed is 8 minus 2 minus 2. And it looks like when we combine these like terms, we end up with 4. Notice, though, this guy is negative, this guy is positive, and as a result, we have opposite signs. That alone says that there has to be some c value in this interval between 1 and 2, such that f of c is equal to 0. Again, also because our function is continuous on that interval. Now, the goal here is to actually identify maybe where is that c value occurring, where it is, in fact, when you throw it in the function, is it 0? Well, let's get a little bit more closer. Let's see what happens if we were to, for example, plug in 1.5. If you throw in 1.5, we end up with negative 0.125. So a pretty close value with 0. Whereas now if you throw in 1.6, we end up with a y value of 0.496. So as you guys can see, we have a negative and a positive in between 1.5 and 1.6. And as a result, we know that it's in between, that c value is in between these two. So then, to be a little bit more exact, we could then go ahead and throw in maybe like 1.51 into the function. Well, when you do that, you end up with a negative value. We're not going to go into the details of what they actually come out to be. And as a result, maybe the next one's going to be positive. Let's go ahead and see if it is in fact positive. It also, in fact, does come out to be negative. Maybe it's going to be between 1.52 and 1.53 instead. So when we throw that in, it does actually, in fact, come out to be a positive value when you throw in 1.53. So you know that it has to be between 1.52 and 1.53. The point of this is really to illustrate that you can actually find zeros simply by throwing values into your function and pretty much just kind of seeing, you know, how close is it to 0. And so you can literally just keep doing this oscillation back and forth until you get a true, not a true, but a very, very solid approximation of what maybe a 0 that you're looking for. And that is, again, pretty much a corollary based off of the intermediate value theorem. So again, though, that is example 7 and the intermediate value theorem from our 1.4 number 2 set of notes.